Bismillahirrahmanirrahim. Assalamu alaikum dear students. This is your instructor Anisa Nawaz from Department of Physics. This is our lecture number 5 from chapter number 1, Measurements. In the previous lecture we have discussed about significant figures, rules of finding significant figures and some simple examples related to significant figures. Okay, so in this lecture first we will elaborate the concept of significant figures, that which numbers are significant and how to count them. Okay, so as we have discussed about rules of significant figures, that non-zero integers are significant. For example, the number 23.32 contains all the numbers which are significant. Trapped zeros or zeros in between two significant digits are significant. For example, 30.025 meters contains two zeros which are significant. Trailing zeros, the zeros at the end of numbers but to the right of the decimal, are significant. For example, 2.00 grams, both zeros are significant. In scientific notation, the figures other than the power of 10 are significant figures. For example, 2.30 into 10 raised to power 5. In this, 2.30 are significant and 10 raised to power 5 is non-significant figures. So we have three significant figures in this value. In integer, number of significant figures depend upon least count of measuring instrument. For example, 2000. It may have 1, 2, 3 or 4 significant figures depending upon least count. And leading zeros are always non-significant. For example, 0.0045. Over here we are having just two significant figures. These were the rules for finding significant figures, and if we have to find out the significant figures in exact numbers, keep this in mind that rules of significant figures does not apply on exact numbers. What are exact numbers? The numbers that are not obtained by measuring, means they are directly coming from some definition, okay, or they are referred to as counting numbers. For example, if we are counting something, like if we are having 12 apples, rules of significant figures will not apply on this counting. Or if we are having 1 inch is equal to 2.54 centimeter, that is an exact number. So rules of significant figures will not apply on these exact numbers. Okay, we have discussed about adding and subtracting significant figures. When measurements are added or subtracted, the answer can contain no more decimal places than the least accurate measurement. It means that in addition and subtraction, the answer is rounded off to the decimal places of the quantity which is having least number of decimal places. For example, if we are having a value which is having a decimal point and we are rounding it to decimals, what we have to do? We start counting just after the decimal point. For example, let's say we are having this value around 17.46789 to 2 decimal places. Okay, because for addition and subtraction of significant figures, we have to round off to some decimal place. So how we are going to round off to 2 decimal places? Let's check this out, that this is the first decimal place and this is the second decimal place, and we have to round off up to this value, 2 decimal places. This will stay a 6 or go to a 7 depending upon what the next number is. We will check out what the next number is. Next number to this 6 is 7. Okay, so this 6 will become 7 and the answer will be 17.47. so it is now rounded off to 2 decimal place. Okay, so after addition and subtraction, we have to round off to minimum number of decimal places in the given values. Another way, if we are going to add some values, like if we are having 150.0 grams and 0.507 grams, how we are going to add these? We will line up the decimal. Okay, we will place the decimal point one on the other. Okay, and then we will add these two values like this. The answer will be 150.507 grams. Okay, you can see over here that 150.0 grams is having least number of decimal places, least number of digits after the decimal. Okay, then we will draw this line after the least number of decimal digits. You can see answer will also contain only this much number of figures after the decimal. So answer will be 150.5 after rounding off. We will check out 150.0 is the least precise, so the answer will have no more than one place to the right of the decimal. Okay, so what will happen over here? The answer will be 150.5 grams. Okay, another example, we are considering some values which have to be added. Again, we are lining up the decimal. Okay, and then we will check out which quantity is having, we will add these values. Okay, we will get this answer, and then we will check out that which quantity is having least number of decimal places. After that, we will draw a line. Okay, you can see over here 18.0 is having least number of decimal places, so we will draw a line after that. It means that the answer will be rounded off to one decimal place, 71.8, but over here correct answer would be 71.9 centimeter, because the last significant figure is 8, and we will round it off by using first number to the right of last significant digit. Okay, so we will round it off as 71.8, because after 8 we are having 7, so 1 will be added to this 8, and we will get the answer 71.9 centimeter. This is the correct answer. So in this way we can add different values and then round them up to the least number of decimal places. This was the rule for addition and subtraction of significant figures. Okay, after that we have discussed about multiplication and division. Answer will be rounded to the same number of significant figures as the component with the least number of significant figures. Over here we will not check out the least number of decimal places, rather we will check out the least number of significant figures according to all the rules which we have already discussed. Okay, so we will round off the answer to the least number of significant figures. How? When we round to significant figures, we start counting as soon as we reach a number that is not 0. Okay, because while we are counting the significant figures, we start counting from the left, and the first significant figure is first non-zero digit. Okay, so again we are taking the value 17.46789, and we have to round it off to two significant figures. It is not two decimal places, rather it is two significant figures. We have to round it off to two significant figures. Okay, see, this is the first significant figure, this one is first significant figure, and 7 is second significant figure. Okay, we have to round off just to two significant figures. So this 7 will remain as 7, or it will become 8 depending upon the next digit. Over here you can see that next digit is 4, less than 5. So this 7 will remain as it is, and what will happen? Rest of the digits will become 0. All the rest of the digits will become 0, and the answer will be 17.00000. All the digits have become 0, and the answer up to two significant figures, it just remains 17. So rounding 17.46789 to two significant figures gives 17. Okay, so let's discuss some more examples of rounding off. Let's say we are having this figure given and we have to round it off to one significant figure. How we are going to round off this number to one significant figure? See, 3 is the first significant figure, so we will round it off to just one significant figure. We will look at the next number. Okay, this next number is greater than 5, so what will happen? It's more than 4. Okay, so what we will do, we will round up, we will add 1 to 3, so this 3 will become 4 and rest of the digits will become 0. So in this way it is rounded off to one significant figure. Okay, another example, round to three significant figures. Check this out, this is third significant figure, 8. So what we will do, we will round off up to three significant figures. We will look at the next number, this is 4, less than 5, so this 8 will remain as it is, and rest of the digits after this 8, after third significant figure, rest of the digits, they will become 0. Okay, so what will happen? 378000, it is rounded to three significant figures. Okay, round to two significant figures, you know that leading zeros are non-significant, so second significant figure is this 8. 2 is first significant figure and 8 is second significant figure. We will check out after this 8, this is 9, so 8 will become 9. What will happen? We will round it up and rest of the digits, they will become 0 or they will vanish. Over here we cannot write this 0, because if we will write 0 over here, that will be significant, because zeros after the decimal are significant if they are trailing zeros. So we will remove that 0 and we will be having 0.0029, which is rounded to 2 significant figures. Okay, let's take a look at example 1.5, part D, page number 19 of your book. We are having this question, 14 into 8. We will get this answer 112. You can see in the given question, the value with least number of significant figures is 8. It is having just one significant figure. So we have to round this 112 up to 1 significant figures. Now, applying the rules of rounding off, we will just keep 1 and rest of the digits will become 0. 1 0 0, okay, or we can write it in scientific notation as 1 into 10 raised to power 2. So we are just having one significant figure in this calculation, just one is there. Okay, so we have rounded it off to least number of significant figures. And while you are doing the example on your neat notebook, you have to write down all the steps, you have to write down all the rules which you are applying theoretically as well. Okay, check out another example, 1.5 part E. We are having these values. We have to multiply these values, 2400, 3.45 and 16.21, and we got the answer 134,218.8. You can see here that two significant figures of 2400 are considered. Okay, we can say it may have 2, 3 or 4 significant figures, but in your book they have considered it equal to 2 significant figures, means least number of significant figures are considered over here, so that we will round off the answer to least number of significant figures. In 3.45 we are having 3 significant figures, and in 16.21 we are having 4 significant figures. Okay, so least number of significant figures over here is 2. We have to round off the answer, which is only allowed to 2 significant figures. So this, what will be happening over here, 134,218.8 will be rounded off to 2 significant figures. Okay, rest of the digits will become 0. So what will happen? We will get the answer equal to 130000, and 3 is kept as it is because the digit after that is 4, which is less than 5. So we will write it as 13 with 4 zeros. Okay, so what will happen over here? We will not write it as 0.0, because 0.0 will give you all the zeros as significant figures. So we will just write it in this way, which will be having 2 significant figures, or you can convert it into scientific notation as well if you want to do it. Okay, hope that is clear now. Okay, let's check out another example, 1.1, page number 5 on your book. Okay, that is related to the topic of radian and steradian supplementary units. Check this out. 2 connected gears are rotating. The smaller gear has a radius of 0.4 meters and the larger gear's radius is 0.7 meter. What is the angle through which the larger gear has rotated when the smaller gear has made one complete rotation? That is example 1.1. You can open your books with you people, and you can write it down step by step on your notebooks as well. Okay, what we will do, first of all we will check out that what is given over here. The way of solving the example, the way of solving the questions is that first you have to check out that what is given in the problem. You have to write down that given data, then you will check out that what is required. You have to write down that required value, and then in the solution you will make the formula. You will select the formula through which you have to solve the question. Okay, so over here we are having 2 connected gears which are rotating. How they are rotating? Okay, you can check this out, that 2 connected gears are rotating like this. One gear is having a smaller radius and the other gear is having larger radius. Okay, you can see that smaller gear is completing its rotation earlier as compared to the larger gear. So this is the way with which the 2 connected gears are rotating. Okay, and we are having a radius of smaller gear which is equal to 0.4 meters and radius of larger gear which is 0.7 meters, and both these gears are rotating. So what we will do, first of all we will write down the given data, given radii of both the gears. You can see what is the way of solving the example. First we will write down the given data. Smaller gears radius, that is given as 0.4 meters, larger gears radius RL which is 0.7 meters. Okay, just these two values are given. So what is the required value? Angle of rotation for larger gear, we have to find out the angle through which larger gear has rotated, theta L. Okay, in solution we have considered this thing that the smaller gear, it is given that the smaller gear performs one complete rotation. So we can write down the theta angle for smaller gear which is equal to 2 pi. So we can say that smaller gear performs one complete rotation, so theta S is equal to 2 pi. So we have written the given data, we have written the required value, and now we are moving to the solution. How we are going to solve it out? You can see that given data is having R, given data is having RS and RL, and required value is theta. So what formula is applied over here? As length of the arc, we know that length of the arc is denoted by S, where S is equal to R theta. We know this relation. Okay, S is equal to R theta. Arc length is equal to radius multiplied by angle in radians. RS into theta S. Name it as equation number 1. By putting values in equation 1, what we will do, we can find out the arc length by putting values in equation number 1. Okay, we know that value of RS is 0.4 meters and theta S is 2 pi. So we will get the answer 0.8 pi meters, or putting the value of pi which is equal to 3.14, we will get the answer equal to 2.51 meters. Name it as equation number 2. So we have obtained the arc length, the length traveled by the gear. Okay, hence arc length S is equal to 2.15 meters. On the larger circle, larger gear would form an angle theta L. So S is equal to 2.5 meters. Both the gears are rotating side by side. So same length will be traveled on the larger gear as well. Same length will be traveled on the larger gear as well. And on the larger gear, larger circle, it will form an angle theta L. So what we will do? We know that S is equal to RL multiplied by theta L. So we will find out, we have to find out theta L. We can write it as S divided by RL. By dividing RL on other side, we will get theta L is equal to S divided by RL. By putting the values, we will get 2.51 meters divided by 0.7 meters. 2.51 meters we have calculated arc length, and 0.7 meters, that was the given value, radius of the larger gear. So we got this value as 3.6 radians. So what we will do, the angle rotated by the larger gear is 3.6 radians. Another extension is given in your book that you have to find out the angle in degrees as well. The angle given over here is in radian, so you can convert angle in degrees as well. Okay, because we know that angle in degrees through which the larger gear has rotated, we know that 2 pi radians is equal to 360 degrees. We know this thing because it is equal to 1 revolution. So 2 pi radians is equal to 360 degrees. If we have to find out 1 radian, then we have to divide 2 pi on the other side. We will get 1 radian is equal to 360 degrees divided by 2 pi. So we will get 3.6 radians. We have to multiply 3.6 on both sides. 3.6 radian is equal to 360 degrees multiplied by 3.6 divided by 2 pi, that is equal to 206.4 degrees. This is the same way, just like you do the problems in maths, that if we are given with the price of 10 pencils, then what is the price of 5 pencils? So first we find the price of 1 pencil and then we multiply it with 5. Just like that we are doing this calculation. First we are checking out 2 pi radians is equal to 360 degrees, then we are finding out degrees in 1 radian, and then we are multiplying both sides with 3.6. So over here 3.6 radians are equal to 206.4 degrees. So we have converted the angle from radians to degrees. Okay. Assignment 1.1, you can check this out in your book as well. A pulley of radius 0.9 meters is used to lift a bucket from the well. If it took 3.6 rotations for the pulley to take water out of the well, how deep is the water in the well? Right now we are just having a single pulley of radius 0.9 meters, okay, and it is used to lift a bucket from the well. This pulley is rotating and it took 3.6 rotations. 3.6 rotations for the pulley to take water out of the well. So we are taking the water out of the well. After 3.6 rotation, water is taken out of the well. We have to check out the depth of the well. That depth of the well should be equal to the arc length. Okay. First we have to write down the given data. Radius of the pulley is given 0.9 meters and number of rotations are also given, which is equal to 3.6. Required is depth of water in the well, which should be equal to the distance, depth of the water, and this should be equal to arc length. Okay. So we can say that as it took 3.6 rotations or revolutions for the pulley to take water out of the well, so we can say that depth of the well is equal to length of arc travelled. Hence S is equal to r theta. Name it as equation number 1, where theta is equal to 3.6 rotations. This is given. We will get 3.6 into 2.2 pi radians. If we are converting it into radians, we will get 3.6 into 2 pi radians. So we will get the answer. After putting it in equation number 1, we will put the value S is equal to 0.9 meters, the value of r, multiplied by 3.6 into 2 pi radians, the value of theta. S is equal to r theta. We will get the answer as 20 meters. So depth of the well is equal to 20 meters. That is our required answer. Okay, so depth of the well is equal to 20 meters after rounding off. Okay, so now we will discuss about another very important article, that is accuracy and precision. We use accuracy and precision in our daily life, but most of the times we are confusing these two terms, that what is the precise value and what is the accurate value. We are not very much clear about this thing. So let's check it out, that what is the difference between precision and accuracy. So what is precision? Basically how well several measurements agree with each other. So precision, what is precision? How well several measurements agree with each other, how close the values are to each other. So you can see over here that how precision, high precision means that all the values are close to each other, and low precision means that the calculated value, the measured values are far away from each other. Okay, so precision is closeness of the value. What is precision? Precision can be of instrument or precision can be of measurement. So let's discuss precision of instrument first. That precision depends upon instrument. Least count of the instrument is called precision. Okay, so least count of the instrument is simply called precision. Smaller the least count, more precise value is obtained. If least count is small, then uncertainty is small and more precise value is obtained. Okay, so precision of instrument, it is simply the least count of the instrument. For example, if we say that precision of meter rule, which is least count of the meter rule, it is 0.1 centimeters. Precision of vernier calipers 0.01 centimeter. Vernier caliper is more precise as compared to meter rule, and precision of screw gauge is 0.001 centimeter. That is even more precise than vernier caliper. So with the passage of time, the precision is decreasing and the values are more and more precise, less uncertainty is there. Okay, so we say that precision is simply the least count of the instrument. So precision depends on the instrument. If you are using different instrument, then different precision is there. Okay, if length of an object is measured with meter rule and the reading lies between 3 centimeter and 5 centimeter, then length of the object is. How we are going to calculate the length of the object which is lying between 3 centimeter and 5 centimeter? We will just subtract these two values. Okay, we can write it as 5 centimeter minus 3 centimeter, which is equal to 2 centimeters. Okay, is it correct? 5 centimeter minus 3 centimeter, which is equal to 2 centimeter? No, this is incorrect way of writing. We have to write it as 2.0 centimeter, because we are measuring this value with meter rule and it is having the least count of 0.01 centimeter, 0.1 centimeter. Okay, so we have to use one digit after the decimal, which is showing its precision. So the correct way of writing the reading taken from meter rule is 2.0 centimeter, not just the 2 centimeter. So just looking at the reading can tell us that which measuring instrument is used. If I am going to write it just the values and I am just going to write down the answer as 2.00 centimeters, then it is telling us that we are using vernier calipers. If we are writing it as 2.000 centimeters, then it is telling us that we are using screw gauge. So the correct way of writing the reading is 2.0 centimeter, because it is telling us about the precision of the measuring instrument. Keep this in mind that we have to write the readings in this particular way. Okay, so second, precision is dependent on measurements as well. Precision depends upon measurement or readings also. Okay, first one was precision of instrument, that was simply least count, but precision depends upon measurements as well. So it refers to closeness of the set of measurements of the same quantity measured in same way. So what is precision of measurements? It is telling us about the closeness of set of measurement, that how close the observed values are to each other. It doesn't matter that whether these values are close to the actual value or not, they should be just closer to each other. Okay, so we say that precision tells about degree of exactness with which measurement is made. So all the times we are getting almost same value, whether it is near to, it is close to actual value or not, it should be closer to each other. For example, we are measuring the length of an object which is giving us as 3.7 centimeter, 3.5 centimeter, 3.6 centimeter. All these values are close to each other. It doesn't matter that what is the actual length, but this calculation, these measurements are precise because they are close to each other. Hope this is clear. What about accuracy? Accuracy is telling us that how close a measurement is to the actual or true value. If we are having this true value, the yellow line, it is telling us the true value and the readings are lying close to the true value, then we will say that our answer is accurate. And low accuracy, if readings are not close to the true value, then we will say that it is having low accuracy. Okay, and measurements should be accurate as well as precise. So while we are taking the measurement, keep this in mind that all the measurements should be accurate as well as precise. Accurate, closer to true value, and precise, closer to each other as well. So we can say that the accuracy describes the closeness of the measured value to the actual value of the measured quantity. So closeness of measured value to actual value is accuracy. Accuracy does not depend upon instrument, it only depends upon measurement. So accuracy has nothing to do with measurement. So if we are measuring the value, the weight of some object which is 100 grams, we are getting the correct reading, then it will be accurate. If we are not getting the correct reading, that will be inaccurate. Okay. It depends upon number of significant figures as well. Accuracy is dependent upon number of significant figures. More significant figures are increasing. What is happening while making the calculation? Okay, so it is only dependent upon the measurement. So what happens? Greater the number of significant figures, better is its accuracy. So accuracy is becoming better if greater number of significant figures are used. So let's check out the difference between accuracy and precision with the help of this video. Okay, check this out, that if we are having precision and accuracy with the help of an archer and bull's eye, we are having a target and archer is hitting the target. You can check this out, that right now all the arrows, they are hitting at the bull's eye, they are hitting the target at the correct position. So these arrows are close to each other as well as close to the actual target. So we will say that this reading is accurate as well as precise. Okay, we will say it is accurate as well as precise. Okay, if the archer is hitting the arrows and it is hitting the target at the same point all the time, but these are not the exact or true value, the true target, so these values will be precise but not accurate. And if the archer is hitting the arrows and they are close to the actual value but they are not very much closer to each other, so these values are accurate but imprecise. They are not precise but they are accurate, closer to actual target but not closer to each other. So we will say that this is accurate but imprecise. And if unfortunately the target all the time, the target is missing and we are hitting all the time at the wrong places, the arrows are not closer to each other or closer to the actual value, then what will happen? The reading will be inaccurate and imprecise. Okay, so this thing can be explained with the help of the start game as well. What is happening? This figure is showing that low accuracy and low precision. Why low accuracy and low precision? Because over here what is happening, all the values are not closer to each other and they are neither close to bull's eye. So what will happen? There is neither accuracy nor precision. Okay, so in this figure what you can see that all the darts land very close together but they are far from the bull's eye. There is precision but not accuracy. What is happening? They are closer to each other but they are not closer to the actual target. So low accuracy and higher precision. Over here you can say that if the darts are spread around the bull's eye, there is mathematical accuracy, but what is happening? Accuracy is there but precision is not there, because these values are not very much close to each other. So high accuracy is there and low precision is there. Okay, and over here darts are landing close to the bull's eye and close together. There is both accuracy and precision. So if values are closer to each other, there is precision. If values are closer to the actual target, actual value, true value, then there is accuracy. Okay, if we are going to explain this thing with the help of graph, what is happening over here? Let's say this red line is showing us the reference value, the true value. Along x-axis we are having the number of different readings which we are taking, values of the different readings which we are taking, and along y-axis we are taking the number of values. Okay, so what will be happening over here? If this red line is closer to this graph, then it will be giving you accuracy. And what is happening? If this graph is narrow, it means the values are lying close together. This will give you precision. If the graph is narrow, that will be indicating precision, values close to each other. But if this graph is lying on this red line, that will show accuracy. Okay, let's discuss different points related to this. Over here, this red line is true value. This first graph A is showing us poor accuracy and poor precision. Why? Because this mean value, this whole graph is not closer to the actual value and we are not having very much values which are closer to each other. So A part is poor accuracy, poor precision. B part, you can see that the graph is lying on this true value. So there is good accuracy, but the graph is wide. We are having different values which are not very close to each other. So we are having good accuracy but poor precision. Part C, you can see over here that values are far away from the true value. So we will say that we are having poor accuracy but we are having a narrow curve, means that values are lying closer to each other. So poor accuracy but good precision. And in the last graph you can see that the values are lying closer to the true value as well as closer to each other. Narrow curve is showing the values closer to each other. So we will say that it is having good accuracy and good precision. Okay, so if we are going to summarize this thing, that what is precision? Precision is dependent upon the instrument, which is simply the least count of the instrument. Precision is simply the least count of the instrument. Okay, and it is dependent upon measured value. How? Closeness of the values. More close the values are, more precise the value is. So this is simply the precision dependent upon instrument as well as measured value, least count and closeness of the values. So we can define precision in two ways: precision of the instrument and precision of the measured values. Accuracy, it is dependent upon measured values, values close to the actual value. It is not dependent upon instrument, it is only dependent upon measured values, values close to actual value, and it is determined by number of significant figures. So we can say that more significant figures, less uncertainty and more accuracy is there. Okay, so I would like to end my lecture with this quote: anyone who has never made a mistake has never tried anything new. Albert Einstein. So if you are making the mistake, if you are doing the things again and again, so that's a good thing, because if you are not making a mistake, it means that you are not trying anything new. So don't be afraid of errors, don't be afraid of mistakes, just keep on trying. Okay, best of luck girls. Thank you so much. That was all for today's lecture.